In this module, let us talk about the basic properties of Bernstein polynomials. Of course, we have to begin with what these Bernstein polynomials are. So fix n greater than or equal to 0. We define the n plus 1 polynomials, or the n plus 1 Bernstein polynomials of degree n defined. Of course, polynomials are defined on the whole of R, but you will understand why I am saying defined on 0, 1 by b kn of x is by definition equal to n choose k times x power k into 1 minus x power n minus k, and this is for k equal to 0, 1, 2, ... n. So given a fixed number n in the natural numbers, there are these n plus 1 polynomials. Each one of them is of degree k, and k runs from 0 to n. Now this is read n choose k. You are familiar with this, I'm sure, from basic probability theory that you have done in your high school. This is just a shortcut for n factorial divided by k factorial into n minus k factorial. Recall that this n choose k, as the terminology says, is nothing but the number of ways in which you can choose k objects from a set of n objects. Okay, so we have now defined these polynomials, but I have said defined on 0, 1. Why do I say defined by 0, 1? Because if you remember your basic probability, what this actually measures is the following. Suppose you have a coin such that probability of heads is x, and of course 0 is less than or equal to x is less than or equal to 1, right? So in a typical coin, we assume that the probability of heads or tails is equal to half. But you can have biased coins where it falls heads all the time. That means the probability of heads is 1, or it never falls heads. That means probability is 0, or anywhere in between. So this is what is known as a biased coin. Suppose you have a biased coin such that the probability of heads is actually x, then you should have no difficulty proving from what you have learnt in your high school that bnk, or rather let me just see the notation, bkn, sorry about that, bkn of x is nothing but the probability of getting exactly k heads with n tosses of a biased coin with p of heads equal to x. Okay, so if this sounds very intuitive and obvious, you can use this to remember what bkn, what the polynomials are, what the formula for the polynomials are. On the other hand, if you are extremely scared of probability, there is another way to remember what these terms bk and x are. Just look at x plus 1 minus x the whole power n. Just look at the whole power n, then bk and x are the various coefficients, or rather the various terms, not the coefficients, various terms in the binomial expansion. This is another way to remember. For instance, let's just write down what it's going to be in the case when n equal to 3. So you just have x plus 1 minus x times 3. Okay, So this is going to be 1 minus x cubed plus 3x times 1 minus x squared plus 3x squared times 1 minus x plus x cubed. Okay, so just look at what bknx is going to be here. We have b03x will be n choose 0 times x bar 0 1 minus x bar n minus 0, so 3 minus 0. Okay, so 3 choose 0 is just 1, so you will just end up with 1 minus x cube, which is exactly what you have in the first term. So now that I think about it, it might be a bit better to write this as 1 minus x plus x the whole cube. I mean, it really makes no difference, but it might be easier to remember if you write it as 1 minus x plus x the whole cube. Okay, so this way you get these 4 Bernstein polynomials. All of them are obviously of degree 3. Okay, so why, I mean, apart from this ease of remembrance, why do you want to write it like this, x plus 1 minus x the whole cube? Well, x plus 1 minus x the whole cube is just 1 cube, which is just 1, right? In fact, in general, x plus 1 minus x the whole power n is just 1, right? So we immediately get the following lemma, which is so obvious from what we have talked about that I'm not even going to bother writing down the proof. Lemma is that the Bernstein polynomials of degree n sum up to 1 for all points x in 0, 1. Okay, now again going back to this probabilistic interpretation that bknx is nothing but the bknx is the probability that you get k heads when you do n tosses with a biased coin with probability of heads being x. This result is obvious because when you toss a biased coin n times, either you're going to get 0 heads, or you're going to get 1 head, or you're going to get 2 or ... n heads. One of them is guaranteed to happen. This is just the sum of the probabilities of getting either 0 heads or 1 heads or 2 heads and so on. So it should obviously sum up to 1. So the probabilistic interpretation also gives you another way to give a proof of this lemma that the Bernstein polynomials of degree n sum up to 1 for all points x in 0, 1. Okay, so we originally started with the goal of approximating an arbitrary continuous function by polynomials. Now I've introduced some polynomials, these Bernstein polynomials, talked about probability and biased coins and n choose k and so on, binomial expansions. What does this have anything to do with approximating an arbitrary function f? Well, it has something to do with it, and that can be seen by this following probabilistic argument. Okay, now if you're not familiar with probability, just listen to what I'm saying, try to understand. If not, it's not a big loss. Please revisit this when you get the opportunity to learn probability theory. None of what I say will actually be needed for the proof, but what I'm about to say is what is guiding the proof. Okay, so what you do is the following. Now fix k, so let me revert back to black. Fix k, in the natural numbers. What we are now going to do is to use probabilistic intuition to figure out what happens to bk comma n of k by n as n approaches infinity. So what we are essentially doing is we are taking a biased coin, not a biased coin. We are going to take various biased coins, each one of which has probability of heads equal to k by n, and analyze what's going to happen if you toss these coins n times and take n to infinity. Now, if you think about it for a few minutes, you will expect this to converge to 1. Why would you expect this? Well, what is bk comma n of k by n? It is nothing but the probability that in n tosses you get k heads when you toss a coin whose probability of getting heads is k by n. But that merely says that if you take a coin whose probability of landing heads is k by n, and if n is very large and you do n tosses, you expect the number of heads to be k. So bk comma n of k by n, as the number of tosses increase, must converge to 1. So this is a bit confusing because n is changing, therefore the coins are also changing. So this is merely an intuition, but it can also be given a rigorous proof, and that is known as the weak law of large numbers in probability. You can justify this rigorously using what is known as the weak law of large numbers, and in fact it is for this reason that Bernstein actually thought that these polynomials could be useful in establishing Weierstrass's approximation theorem. So if you don't understand why k comma n of k by 1 must actually converge to 1, it's really not that important, because in the proof anyway we will establish that in a self-contained manner using just real analysis. But what I'm about to say now will seem very confusing if you don't understand this. B k comma n of x will be very small if x is far away from k by n. Okay, so what this is saying is, we saw previously that bk comma n of k by n converges to 1 as n tends to infinity. On the other hand, bkn of x will be very small if x is far away from k by n. Let me put this far away in quotes. Okay, so both of these, please think about it in intuitive probabilistic terms. We will anyway establish all this rigorously. This is just the basic idea. So what we will now do is, we will use these Bernstein polynomials and sample values of the function f, and use those sampled values to show that you can get a polynomial that converges uniformly to the function f. So what we do is the following. Let f from close 0 1 to r be continuous. We define the degree n Bernstein polynomial. Note there is only one such polynomial, Bernstein polynomial of f, to be, as you can guess, is just going to be Bnf of x is summation k equals 0 to n. So essentially you are going to sum up over all the Bernstein polynomials of degree n. You sample the values of f at k by n and multiply it by bkn of x. Okay, which is nothing but summation k equal to 0 to n f of k by n, and expanding out bkn x, you get n choose k x bar k 1 minus x bar n minus k. These polynomials b and f are the Bernstein polynomials of degree n. So what does our probabilistic intuition tell us? Well, if you look at this sum for any value x, what will happen is, as you increase n, then from the intuition that we have seen before, this f of k by n, this value is getting weighed by bkn of x. When x is very, very close to k by n, this quantity bkn of x will be very, very close to 1, and the value f of k by n will be completely got. Whereas for those k by n's which are far away from x, these terms bkn of x will be 0 and they will contribute nothing to the sum. Okay, so essentially we will get the sampled value of f at k by n. So this is all sounding a bit vague, but don't worry, we will make it precise. So what this discussion suggests is that to complete the proof, of course, if it's not clear, we are going to prove that B and Fx converges to F uniformly on 0, 1. On 0, 1. That's the aim. What we will do is, we will split our analysis into two parts. We will study where x minus k by n modulus is small, and number 2 where x minus k by n is large. We will split our proof into two parts and handle these two parts separately. Okay. In fact, for the first part, just uniform continuity will give us what we need. Recall that a function defined on a closed interval is automatically uniformly continuous. So f is uniformly continuous. For the second part, we need some properties. Of Bernstein polynomials. Some special properties of Bernstein polynomials are required to handle this case when x minus k by n is large. As you can expect, we have just done everything very vaguely and intuitively, so it might look like the proof is over, but actually we have to do some analysis to make my vague remarks precise. So this is the motivation behind the proof. If you don't understand a substantial amount of this, it's not at all an issue, because the proof is not going to actually require this intuition. The proof is self-contained, but the ideas behind the proof are motivated by the intuition what I have spoken about in this module. In the next module, let's prove some basic identities of the Bernstein polynomials that will be needed in the final proof.